Hello students, in this video I am going to explain UJT circuit operation with necessary diagrams, VI characteristics curve and equation. In VTU paper you may get this question for 8 marks and the expected answer should be in this format: circuit diagram which carries 2 marks, VI characteristics 2 marks. So all the information will be shared with the equal weightage. So let's proceed to understand the unijunction transistor. As the name implies, unijunction, that means it has one single junction. So where this single junction you may find in the solid structure, in the solid state device of the UJT, you may find here there is a two materials used. The two materials are, one is N-type lightly doped material and P junction heavily doped material. And there are three terminals here. One is B1, base 1 layer, and base 2 layers, which is connected to the N-type bar through the ohmic contact. As you know that ohmic contact is a very good interface, that is conductor layer and semiconductor layer. And we are going to introduce one P junction here, P material here. So this forms PN junction. So when we interface P material to the N type bar, so it creates one barrier that is called PN junction, which is a uni junction. A single junction exists in this emitter to B1 layer or emitter to N type bar, we can say. Okay. So in this way, it is uni-junction transistor. So there are three terminals in this device, that is B1 layer, B2 and emitter. Okay. So when we go further to understand the symbol, globally accepted symbol, so it looks like a MOSFET, but here we have B1 layer, B2 layer and emitter layer, and the inclination for this arrow marks towards the B1 layer. Why this? I'll let you know using a equivalent circuit diagram. In the equivalent circuit diagram, you may see here the P and N junction exists, which is shown in this equivalent diagram as a diode. So there is a diode D1 present in this emitter terminal, emitter to the N-type bar. There is a difference in the resistance found in this upper N-type here, in the upper N-type bar and the lower N-type bar. You may find two different resistors. When you are going to find two different resistance, that is explained in the UJT operation. It is very simple to understand the behavior of the UJT. When D1 diode is reverse biased, you may see here the RB1 value. The resistor which is shown near to the base terminal is going to be 4 kilo ohm. Very large resistance seen across that particular layer. So at that time we say UJT is in off state. Okay, when diode is reverse biased, that this resistance is very high and we say UJT is in off state. When D1 is forward biased, as you can see, RB1 decreases to a large extent, 4 kilo ohm to 10 ohms. So very small resistance it is going to create here in this layer. So current starts flowing at that time. So UJT is on state. We can say UJT is on. So there exist two different resistance can be measured by using equivalent value. There is RBB, so which can be nothing but at the off state you can measure this value RB1 and RB2, likely to be 4 kilo ohm to 10 kilo ohm. Okay. Further, so as you know, RB1 varies during the operation from 4 kilo ohm to 10 ohms. Further, you may see when the UJT is connected with the two power supplies, that means it is biased now. So when one of the supply is connected to the emitter terminal named as VEE, through the RE resistance it is connected to emitter point. Okay. Similarly, the VBB is connected to the base 2 terminal and the negative is connected to the especially B1 terminal. So you may see here how the transistor biasing is done, especially at the input side we have made it as forward biased, and at the at the other end, that the output side we made it as a reverse bias. How? Simple. You know that the B1 and B2 layer is formed through the N-type material. So the positive terminal is connected to the N layer. So there is a N layer here. So since the positive is connected to the N terminal, makes it as a reverse bias. Okay. Similarly here, the emitter terminal, which is through the P material, we have formed a emitter terminal here, which is connected to the positive. So P material is connected to the positive terminal. So this makes forward bias. As you know, the thumb rule of the transistor, operate the transistor. So we are supposed to properly bias it. So how to bias it? So we have to make forward bias. Input side should be forward bias. Output side should be reverse bias. So this is the first thumb rule we have to follow to operate the UJT. Okay. Further, when it is in off state, let's try to measure what is the voltage seen at this node Vx. Okay, you can easily apply the voltage divider theorem to find what is the voltage exist when it is in off state. Okay, when it is in off state, you can apply voltage divider theorem and you can easily find out what is that value. So you know that as per the voltage divider theorem, the Vx will be measured with respect to the ground across RB1. So that comes in the numerator to the total resistance RB1 and RB2. RB1 plus RB2 multiplies by the main supply voltage, that is VBB. Okay, so this RB1 divided by this can be written as RB1 divided by RBB. So your RB1 plus RB2 can be summed up as one term, that is RBB. Okay, so that is used as RBB here. Vx, what is Vx? Vx can be written as neta times the VBB. So this whole term I'm going to substitute as neta value. So where neta is nothing but neta is the intrinsic standoff ratio. That is, it varies from 0.5 to zero point 0.8. So if you want to measure the peak voltage, which can be measured as Vx, that is Vx just be found by applying the voltage divider theorem, Vx plus Vd, because there is a voltage here also, so there barrier voltage is there. So to turn on this particular device or diode, we require 0.6. So that's why your peak voltage is nothing but can be calculated as Vx plus Vd. Vx can be written as neta times the VBB plus Vd, right? So if you want to, when we apply the VE by keeping VBB constant, so VBB is kept constant here. You may observe here, that is 20 volts we have kept constant. Okay, because in this expression you may see VP is purely dependent on VBB. It is directly proportional. As you vary the VBB, or peak voltage is going to vary. So that is going to alter your VI characteristics. Okay. For the characteristics of a UJT, you may see there are three regions. So first, one very important observation here in the VA characteristics is the VBB is kept constant, which is 20 volts. And let's try to substitute this value when UJT is in off state. So by using VP expression, VP is, which is nothing but a peak voltage, is purely determined by using this expression neta VBB plus VD. So your VP is decided by the VBB factor. Say neta is, as you know that neta varies from 0.5 to 0.8. Now let's keep the value neta as 0.65 and VBB is 20. The peak voltage is going to be 13.5 volts. Till 13.5 volts, your UJT is in off state. It is in cutoff state. Soon after the particular value, a small variation after the VP, suddenly it enters to the next region, that is called negative resistance region. In the negative resistance region, the current increases, voltage decreases. So once it reaches to this particular 2 volts, that is called valley point, current increases from 5 milli to 50 ampere. Initially, when in the cutoff state or below that, you are going to find in microampere. So it is also called as cutoff state. Okay. So till the peak voltage, you are going to get cutoff region. And once after the cutoff, especially after the peak voltage, once we set, so it is going to enter to the negative resistance region. So in the negative resistance region, you may find increase in the value from 6 micro to 5 milliampere, and the deflection is seen. That deflection is called valley point. After the VV, that is 2 volt, and it may go up to this particular 50 milliampere. A very large current being seen at this particular saturation region. Further, so you can also say that your UJT is in off state and on state based on when IE is zero. IE is zero when IE is zero. So in the cutoff region, almost IE is less than 6 microampere. So we can treat that as zero. So all the applied voltage, that is VE, will be seen across it. Okay, VE become VE. So when the UJT is in on state, VE becomes VB. So that is value voltage. VE becomes value voltage. No matter you may increase the value, so suddenly the voltage will not move further. So it becomes VV. And at that time, IE is greater than 0. Again, it is limited by RE. Further, you can see that where IV is nothing but valley current, or it is also called as holding current. Okay, this IV, which is 5 milliampere, is a holding current below which the UJT goes to turn off state. Okay, so it has to be so this you have to hold this value if you want to make UJT on. Okay, similarly, VP is nothing but peak voltage. So the peak voltage is purely determined by this expression neta times the VBB plus VD. So when IE is decreased below IB, UJT enters to turn off state.